What's happening, guys? Hope you're having a great day. Of course you are. We're learning about physics, right? Anyway, all jokes aside, today we're going to be talking about Newton's laws, or more specifically, we're going to be solving some problems using Newton's laws. So if you haven't seen that video where I explain some of the basics of Newton's laws, then go ahead and look in the description. There will be a link there. Go ahead and check out that video, and it's going to kind of give you a basic intro to Newton's laws. And in this video, we're going to be solving a bunch of problems using them. And it's not going to go too long, because once you get the hang of how to solve these problems, they really aren't that difficult. So let's go ahead and get started. 1. An astronaut throws a baseball at an initial velocity of 5 meters per second towards Mars. Assuming the nearby gravitational fields are negligible, what will the velocity of the ball be after 20 seconds? So, on first glance, this seems like something you might check your kinematics list of formulas for, to start comparing variables that you know with what you need to know. But if you take another look at it, it actually is going to be much easier than that. See, we see here that the initial velocity is 5 meters per second in some really kind of arbitrary direction. So we can really choose whatever coordinate system we want when we're looking at this here. And we're assuming that the nearby gravitational fields are negligible. So essentially what that's saying is that any force of gravity that ball might feel, we can assume that it's not there. We can assume that there is no force from gravity, which is very nice, because especially where we don't really know how far we are from other things, it's good to know that we don't have to factor in those forces of gravity. And essentially it's just asking, what is the velocity of the ball after 20 seconds? Well, if we look closer, there really isn't a net force on this ball, because at first the astronaut throws the baseball, right? And that expends a force on the ball, but after the ball is released, there is no net force. We can discount any air resistance because, well, in space there is no air. And since we can discount gravitational fields, there is no force of gravity in any direction. So essentially, what this problem is saying, the setup is, there is no net force. So if we were going to draw a free body diagram, we would see that there is no net force here. Whichever way you spin it, there's no gravitational force and there's no other force happening. So if we think back to Newton's laws, we know that by Newton's first law, that if something is in motion or at rest, and it will continue in that state of motion until it's acted upon by another external force. And unless there's another force happening within that 20 seconds, by Newton's first law, this ball isn't going to change its state of motion. It's going to stay going at the exact same velocity, or its acceleration is going to be 0. So, since they don't say that the velocity or that anything is going to happen to that ball in that 20 seconds, we can assume that nothing is going to happen to it. So, the velocity of the ball after 20 seconds is going to be 5 meters per second towards Mars. And this is really just based on the idea that if there is no external force on an object, it's going to stay doing what it's doing forever, essentially. So that was pretty easy. Let's go ahead and look at this next one. A woman pushes on her on a broken down car with 1,000 newtons of force. It doesn't move. How much force is the car pushing on her with? Now this is something that you think, oh shoot, I'm only given one number really, and just some qualitative information. How am I supposed to solve this? Well, if we think back to Newton's third law, which says that every action causes an equal and opposite reaction, or that if two things are in contact, one thing pushes on the other thing just as much as it's being pushed on. So in this situation, we see a woman is pushing on her car with a certain amount of force. It doesn't move part here is really kind of irrelevant, because as long as the woman and her car are in contact, they're going to be exerting the exact same force on each other as they are feeling. So here's that woman, and here's her car. And let me lengthen her arm there. So they're in contact. And again, if we were to split this up, we would see that the force from the car on the woman is towards the woman, and we would see that the force on the car from the woman is in the exact same opposite direction. But even though I drew it a little bit out of scale here, we would see that they're the same magnitude, but just in the opposite direction. So if we think about it again, how much force is the car pushing on her with? Well, if they're in contact, then the car is pushing on her with the exact same amount of force she's pushing on the car with, or 1,000 newtons. So again, this is just another easy application of Newton's laws. 3. A bowling ball with mass 5 kilograms was released from 100 meters in the air. Assuming air resistance is negligible, what is the net force on the ball in free fall? Now this is another one you might think, okay, well let me check my list of formulas, let's see, and start plugging in variables. But no, if we think about it, if air resistance is negligible, then the only force acting on that ball is gravity. And we know things about gravity. We know the acceleration due to gravity, close to the surface of the Earth. So at this point, we can just start applying Newton's second law. F equals ma. And so here we're solving for the net force, F, and we have mass, and we know acceleration because the only force acting on this ball is gravity. So we can just fill it in immediately. It's already solved for us. So the net force, is equal to the mass, 5 kilograms, and yes, it is in SI units, so we're good there. And you should know by now that the acceleration due to gravity near the surface of the Earth is approximately 9.8 meters per second squared. So we'll just put 9.8 there. And then at this point, all we do is just multiply them together. And it comes out to about 49 newtons. So again, just a quick application of Newton's laws, and we're all set. 4. A basketball strikes the backboard of the net and goes flying back straight towards the player who threw it. When the player catches it, the ball has a velocity of 3 meters per second. What is the ratio of the force on the ball from the backboard to the force on the backboard from the ball? So essentially, this question is just asking how do these two forces compare? And it's in kind of a roundabout way, and of course they phrase it in a kind of difficult to understand and wrap your head around way. But if we break it down and we see that we have a contact between the backboard and the basketball here, and the player catches it, the ball has a velocity of 3 meters per second, is really irrelevant at this point. We just see that they're asking for the force on the ball from the backboard and the force on the backboard from the ball. Whenever you see that kind of that parity or that similarity in the phrasing here, you should immediately think about Newton's third law, because they're asking about what's called a Newton's force law pair. Newton's third law of force pair, excuse me. And this is really just saying that they're the same amount of force, the same magnitude of force, they're just in opposite directions. So again, if we were to look at it, like here's the backboard with the net, and here's the basketball bouncing off that direction, that if we were to break it up, we would see that the force on the backboard from the ball would be in this direction, and the force on the ball from the backboard opposite direction, but same magnitude. So at this point, we're just finalizing our answer, and we know that they're just asking for the ratio of the forces. So And since we know that the magnitude is the same, it's really going to be simple. We don't have to calculate anything, and that's good because we don't really have any information on how to calculate that force. But we do know by Newton's third law that this placeholder for force here, we can say on the ball from the backboard, so B doesn't really matter, but to the force on the backboard from the ball is going to be the negative ratio of 1 to 1. Because although that they are the same magnitude, they're in the opposite direction, so that's going to give us a negative sign, but this ratio is 1 to 1, or comes out to -1. So this is pretty simple. You just have to be careful about your how you phrase your answer, because maybe they're just asking for 1, maybe they're asking for -1. You just have to be very careful of your coordinate system. Number 5, a machine is starting to push a heavy box across a warehouse. The net force is 100 newtons and the resultant acceleration is 2 meters per second squared. And what is the mass of the box? So by this point, this should kind of trip your Newton's second law alarms in your head. Now we know the acceleration and we know the force, so we just have to plug it in to Newton's second law here. Force equals mass times acceleration. And we're looking for the mass, so we're just going to solve this, which will give us mass equals force over acceleration, which is going to come out to be 100 newtons over 2 meters per second squared, and that's going to give us 50 kilograms. Now it will be in SI units, kilograms, because here we have SI units of newtons and SI units of meters per second squared. So if you plug all SI units into a formula, you're guaranteed to get SI units out. So that will be the correct answer. So the box is 50 kilograms, has a mass of 50 kilograms. And finally, here we have a hockey puck is sliding on ideal ice, or it has no friction, at a speed of 8 meters per second. How far from the initial position will it stop? Now this is another one where you might say, okay, well, it looks kind of like a kinematics problem. I know there's one of the formulas that, gives position or difference between initial and final position, and I'm pretty sure I can plug everything in, but no, this is very simple. We see here that it's sliding on ideal ice or has no friction. And also, because of the low profile of a hockey puck, we can assume that there is no air resistance, or really not enough to make any difference. So the speed of 8 meters per second is going to be constant, because if there's no net force, then there's going to be no change or no acceleration, or no change in velocity or change in speed. So that speed of 8 meters per second, since there's no other force acting, is going to be constant. It's not going to change. It's going to stay in its state of motion. So if the ice rink or the lake or whatever is infinite, if the puck has an infinite amount of space to travel, then the distance is infinite. It may never stop. If the ice were to go off into infinity, then the puck would just go right off into infinity. So it really just depends, and it's just one of those trick questions that you should take a look at and say, okay, well, do I really need to plug in things into an equation, or can I use one of these laws to find what's going to happen, to find the answer pretty easily without even needing to solve quantitatively? So I hope you learned a lot. If you did, please leave a like. If you want to see something else, leave a comment with what you would like to see. And for more physics videos, please subscribe. Have a great day.